So welcome everybody to the third panel discussion in the INT program, Scientific Quantum Computing and Simulation on Near-Term Devices. Today's panel is focused on quantum directions for nuclear and particle physics. We have a great panel and moderator to discuss the subject today. Today's moderator is Christine Muschik. So Christine's on the faculty of the Institute for Quantum Computing in the University of Waterloo. She earned her PhD in Ignacio Serac's Max Planck Institute in Munich on quantum processing with atoms and photons. She was a Humboldt postdoctoral fellow in Barcelona and then followed by a postdoctoral position in Peter Zoller's group in Innsbruck. She's worked on a diverse array of areas related to quantum information science, including the simulation of topological systems, entanglement, quantum memory and sensing, error correction, quantum communication, and quantum simulation of quantum field theories and fundamental symmetries. Her co-authored paper on trapped ion simulations of the Schwinger model in 2016 was remarkably influential in activities in nuclear and particle physics in the United States. And so without further ado, I turn the floor over to Christine.
Thank you. Thank you, Martin. And big welcome to everybody also from me. Welcome to today's panel discussion. So today we will have 3 30-minute blocks adding up to 1.5 hours. And our block number 1, in our first block, each panelist will have 5 minutes to introduce themselves and to share their ideas. And then in block number 2, I will guide a discussion. And then finally in block number 3, you, the audience, will have the opportunity to ask questions to our panel. And as Martin said, our topic for today is quantum directions for nuclear and particle physics. And yeah, I'm excited because that's a topic that I am personally very interested in. So it has been both a focus and a passion for me during the last couple of years. So I work mostly in quantum simulation, quantum computing, but today's discussion is much broader than that. It's really about quantum methods, which includes also quantum-inspired algorithms on classical computers and also quantum technology in terms of, for instance, quantum sensors that can offer quantum advantage for high-precision measurement tasks. And like these very broad questions will be discussed by a great panel. And so we will start now with the introduction of our panel, and I will go through all the panelists, introducing them, and then each panelist then has the opportunity to give their 5-minute statement. And so order will be, we start with Joe Formaggio, then Doug Beck, next one Zohreh Davoudi, then Dima, and Joe Carlson in the end. So let's start with Joseph Formaggio, Mr. Neutrino. So Mr. Neutrino got his bachelor degree at Yale and PhD at Columbia University on neutrino physics, of course. And then he did his postdoc at the Sudbury Neutrino Observatory and also became an assistant professor there. He moved on to become an MIT associate professor, and now he's still at MIT and became the division head of the experimental nuclear and particle physics part. So Joe explores the nature of neutrinos and connections between particle physics and cosmology. And among the experimental efforts, I'd like to point out 2. Snow Lab, because it's here in Ontario, and also he contributes to the construction of an experiment, a future experiment called Katrin, which is in Germany. So Joe, for your first 5-minute statement, I'm especially interested to hear which areas for quantum methods you can envision to be really beneficial and to have an impact for nuclear and particle physics. So Joe, the floor is yours.
Thank you, Christine, and hello to everyone who's joined in. It is It's a great pleasure to be here and participate in this panel discussion. What I offer are just my own musings and thoughts, so please take them with a grain of salt. Yes, so I have embarked in, I've been in nuclear and particle physics, since grad school. As Christine mentioned, it's been neutrinos pretty much the whole way, starting with very high energy neutrinos at the beginning, and then looking at solar neutrinos through SNO, and now exploring neutrino masses at very small scales. So I keep descending down in energy scale for each time. It's only been recently that I have been intertwined with quantum methods and the quantum community, mainly because I saw that there was potential for nuclear physics, or some of the projects that I was involved in specifically in benefiting from the technology that had been developed thanks to years of R&D on the quantum initiative side. Certainly, I'm sure we will hear a lot about quantum simulations and algorithms. I'm not a theorist, so I can only speculate mildly on them. However, on the issue of quantum sensors, I see actually great potential for collaboration and mutual growth between the two communities. And the reason for that is because certain aspects of nuclear physics and particle physics benefit from exquisite precision for very low energy signals or triggers for seeing rare or beyond standard model events. I highlight two particular ones. As some of you may know, there's an increasing exploration of the space for very light dark matter in order to understand the dark matter question in the universe. What is dark matter? What is it made of? Is it WIMPs? Is it very, very light particles? Is it axions? And there is one parameter space that's exploring extremely heavy dark matter candidates, either through high energy collisions or very large underground experiments. But there is an increasingly interesting parameter space with very light particles. Either these are still weakly interacting particles, or they are axions, which are conjectured in various extensions of the standard model. And the signatures for each of these tend to mimic the kinds of signals that technologies that were developed for quantum calculations. It's in their regime, and so the ability of either using new types of sensors or even just the technology that's already been defined for those fields would allow us to push in that direction. So again, it's not entirely like all of nuclear physics and particle physics, is going to move in this direction, but there are certain places where the added advantage of having high precision ability to see, single photons, single quasi-particle events it would be a signature for new physics. And one of the bedrocks for nuclear physics and particle physics is finding new phenomena and new extensions to the standard model. And this is an opportunity to develop those tools and expand our sensitivity in these regimes. I think I used my phone.
Okay, great. Thank you. Thanks a lot. That was very interesting and exactly 5 minutes, like perfect.
All right.
So then let's move on to Douglas Beck, who got his bachelor in Canada and his PhD at MIT. Had a very successful postdoc at Caltech and is now full professor at the University of Illinois. Doug is the lead and actually the creator of the G0 experiment. So it's a big effort. It has like 80 collaborators from 18 institutions, and it's a study of strange quarks. And yeah, more broadly speaking, apart from that, Doug is an expert in high precision measurements. And he embarked, for example, on the challenging quest to measure the neutron electric dipole moment, which is, of course, an endeavor that is also tied to yeah, very deep question, like the question why everything we see around us is made of matter and why we enjoy such a striking matter-antimatter imbalance. And yeah, without further ado, Doug, I'm looking forward to your 5-minute statement, and I'm especially interested to hear whether you know any favor any specific or concrete problems that would benefit from quantum.
Okay, well, thank you very much for the kind introduction, Christine. I'm going to share my screen here. Let's see if I can do this.
That works.
Full screen. Good. Okay, so again, welcome to everyone. And I'm also looking forward to a good discussion today. I think that the starting point for me in thinking about quantum information and nuclear physics is that nuclear physics really is a study that is based on many body quantum mechanics. And for example, I think it may be that entanglement plays some role in some roles, probably in nuclear physics that we haven't yet completely understood. I think there are a number of sort of obvious opportunities here, and I've just listed some of them. I believe that there'll be opportunities in simulation, both digital and perhaps more than is generally recognized in analog simulation. Simulations using cold atoms, for example, where strong nucleon-nucleon interactions can be modeled in unitary systems. But in particular, moving to problems that we've had a hard time solving in nuclear physics: non-zero density, time-dependent problems, strong coupling problems of various kinds, and in particular, things like hadronization, of which there's going to be a lot in our future as we move as a community toward the EIC. Joe gave a very nice summary of the opportunities with quantum detectors, its sensitivity and precision, and I think that that will be continue to be an expanding field. There are, I think, in return, some opportunities for quantum information science, perhaps to take advantage of detectors that might be developed for nuclear and particle physics, further developed for nuclear and particle physics, let's say, to support simulation platforms of one kind or another, detecting photons, and so on. And I think from the theory side, frameworks for error correction, which is almost certainly going to have to be in our future in some form or another, I think there'll probably be those frameworks will be informed by work on field theories of various kinds, and perhaps the theorists will address the issue. But for an opening statement, I'd like to try to broaden things a little bit. we often take advantage of quantum mechanics more generally in our experiments. The G0 experiment that Christine mentioned was a parity violation experiment, and that was a way to use quantum mechanical interference to find a small effect. The weak interaction, which is normally swamped by the electromagnetic interaction of electrons and nuclei. And so we were able to take advantage of quantum mechanics in that experiment. So to try to illustrate this point, I want to talk about something that I don't do, but that I find quite interesting and has some connection to Christine's institution at Waterloo. I want to talk a little bit about neutron interferometry, which started, or at least this batch of things that I'm going to talk about started with Sam Werner many years ago, 1975, in a completely different era. It started at the Ford Motor Company, interestingly, and where there was still a research division. He eventually moved to the University of Missouri. But the idea was to basically reproduce what one could do with photons in a Mach-Zehnder interferometer, to do that with massive particles. And so they built interferometers out of single crystals of silicon that were sort of the scale of 20 centimeters, perhaps, something like that. And you can see in the sketch there at the bottom these blades that are hatched in. They would stick up above a base, which is this single crystal. And so they were able to demonstrate, for example, quantum mechanical interference. They could make a signal go away essentially from this interferometer by putting a piece of material on one of the paths of the interferometer, and then simply by changing the scattering length, the sign of the scattering length of that sample, putting in two samples, one with a positive scattering length, one with a negative scattering length, they were able to recover the contrast back to what it was. And so a nice demonstration of the simple quantum mechanical interference of neutrons. And so this setup sort of developed through the last 45 years. At some point along the path, people entangled spins and positions and pursued a number of measurements in fundamental quantum mechanics. And so more recently, this has some of this research some of it's still being done by people in Vienna at the ILL in Grenoble, where I am working on an EDM experiment. But as I said, David Corey and Dmitry Pushin from Waterloo, together with Michael Huber at NIST, are investigating new ways of doing neutron interferometry. And in fact, imagining that one could take that single crystal device and split it into two pieces and make it much larger. And so the and in addition, developing a new tool, which is a sort of a straight through interferometer that works sort of like straight through holography. And that's the illustration in the bottom right of the slide. And this has the advantage that the neutron intensity can be much, much larger, many factors of 10, orders of magnitude. And in addition, one can prepare now neutrons in various kinds of states with quantized angular momentum, quantized orbital angular momentum, and then coupling that angular momentum, orbital angular momentum, to spin angular momentum. And it allows one to study, for example, materials with particular kinds of structure and of interest to the QIS community, in particular topological materials with the certain rotational symmetries. But the bottom line here that I wanted to point out is that this new generation of neutron interferometry really is starting to look like a digital quantum simulation. One prepares, I don't know whether you can see, it's off the bottom of the slide perhaps for you, but one prepares an initial state where in principle one can entangle neutrons. You propagate them through some system, through some filters, if you like, and at the end, you make a measurement. And you might think about making a weak measurement. You might think about doing some post-selection and so on. And so I'd like to suggest that we continue to think about all the parts of quantum mechanics that we've been able to make use of over the years and see how they might fit in with current thinking about quantum information. So
yes, thank you. Thank you. So that was very concrete. Thanks. So with this, the next one to share her statement is Zohreh Davoudi, and she did her PhD at the University of Washington, actually, then moved on to a postdoc at MIT. She's now an assistant professor at the University of Maryland, but also associated with RIKEN, with their research program. And yeah, she got awards and recognitions for her exciting work. So in 2018, the Kenneth Wilson Award in Lattice Gauge Theory. And then just last year, even 2 prizes, the DOE Early Career Award and the Alfred Sloan Research Fellowship. So she studies effective field theories and lattice chromodynamics, but she's also bridging over, like directly in her research, to quantum simulations and quantum computing. And yeah, I'm looking forward, Zohreh, to your statement.
Thanks very much, Kristen, for a nice introduction. Very excited to be here on this panel and share some views and also learn from many great participants about their views. So it's unfortunate that we can't be at the Institute. We all miss INT and the nice environment. So hopefully this will be over soon and we all meet at the Institute. So this is just a quick perspective on my sort of take on where we should be going. And this is going to be concerning the quantum simulation aspect of the quantum information science. So I'm not going to be touching much on some of the things that, very interesting things that we already heard on the, for example, sensing aspect of this program. From the perspective of simulations, what we have in mind is to be able to leverage the systems that have drastically different length scales or even sort of effective degrees of freedom, such as the atoms, molecules, and quantum matter, to be able to describe systems that we're interested in: nuclear physics, quarks and gluons and nucleons, and maybe a nucleus or some dense form of matter, such as that in the neutron star, and sort of leverage the systems through some digital quantum computations or more naturally through an analog quantum simulations of these systems. So this is really at the heart of problem. How do we leverage these systems to describe fundamentally different systems in nuclear physics? Some of these interesting problems that we would like to address, Doug already mentioned it, but very quickly, we have been very much limited in our classical algorithms through lattice gauge theory methods to study systems that have a finite chemical potential, finite density. And this is also a problem with ab initio nuclear many-body methods. So we very much would like to, from first principles, study and understand, for example, the phases of matter and this QCD phase diagram that is sort of conjectured to have very interesting phases. And of course, there is a lot of interesting physics that we probably are missing because we have been also limited to static problems. So if you're interested in real-time dynamics of matter, and in principle, any quantity in physics that is being defined, particularly through the Minkowski spacetime definition, such as dynamical response functions, transport properties, hadron distribution functions, and all the sort of non-equilibrium physics of QCD, we will not be able to really address them with the current technologies in our classical simulations. So the goal is to be able to really reach out and use new technologies to think about these problems as well. So the kind of a nuclear physics roadmap for leveraging quantum technologies, I would think should look like what we have been sort of following in the classical simulation side of things, where we think about this sort of multi-level matching program between the standard model degrees of freedom and QCD, down to effective field theories of nuclear physics that can be matched to a standard model or lattice QCD calculations of these observables in the few-body system. And these effective field theories, or even the phenomenological models of nuclear physics, they can be constrained and then used in the many-body nuclear structure and reaction calculations, which basically solve this complicated quantum many-body problem. And then you can understand and start to address some of the interesting questions in the many-body area of nuclear physics, such as the properties of matter and neutron stars, and tests of a standard model and violations of symmetries of a standard model in searches for new physics, and so on and so forth, right? But the goal now is for the quantum simulation program, if we can somehow leverage quantum simulation and quantum technologies, one path we can imagine is to start from quantum field theories of nature, from a standard model, kind of directly simulate those, and then get to physics that you're interested in. Or you can imagine that we would still need these effective field theories or phenomenological models to study sort of few-body systems that is kind of facilitated by quantum technologies, and then feed to many-body nuclear structure calculations. And they can also then facilitate this many-body problem by leveraging the quantum computations and quantum simulation and get to the physics that we're interested in. So I can think about these two paths. And of course, whether you take the first path or the second path, there are various components to this program. There has to be a lot of theory developments. There's going to be a lot of algorithmic developments, as well as a research on implementation and benchmark, because otherwise you're going to be sort of detached from what's going on out there in terms of realistic hardware and how these hardware are going to be developed for the particular problem that you're interested in. So all of these have to happen at the same time. And there's been quite great progress actually in the past few years on addressing each aspect of this quantum simulation program. Just kind of quickly, I want to mention that kind of problems that we have to deal with in nuclear physics and strong interaction physics, they are kind of different from problems that traditionally the quantum computational scientists have been dealing with in quantum chemistry or condensed matter physics and spin systems. And the reason is simple. Even if you start from the nuclear Hamiltonian, where the degrees of freedom of nucleons, you're going to be dealing with more complex Hamiltonians. The Hamiltonian itself might not be even known with arbitrary accuracy, and that's the role of effective field theories and all these models and matching to QCD and experiment to be able to give you more trust in these Hamiltonians. The Hamiltonian itself can have short, intermediate, or long-range interactions. And they're gonna have 3 and multi-body interactions, something that, for example, quantum chemists don't have to deal with. There's going to be pions and other hadrons that can become bidynamicals and all these sort of complications that we have to deal with in the quantum simulation as well. if you start from the standard model and quantum field theories of a standard model, then it's even more different and more complicated, because now you have both bosonic and fermionic degrees of freedom to start with. These are dynamical and coupled. And more importantly, they exhibit both local and global symmetries. They are relativistic systems, so the particle number is not conserved. And vacuum itself is non-trivial in this strongly interacting theory. So we have to make sure that all these features are being represented in the quantum simulators that we're designing for these systems. The very sort of last point, last 30 seconds, I just want to say that there are a lot of different areas and directions we can think about, right? And a very important thing to notice is that, again, just similar to the classical computational approach to nuclear physics, we have to identify the right degrees of freedom for the given problem that we're interested in. We have to make sure that we also leverage our classical computing capabilities. So maybe in the near term, we have to think about sort of these hybrid classical quantum approaches to our problems. We should also talk to experimentalists. That's very important. Maybe we can impact the in a co-development process, the development of these hardwares that are going to be in market and make them more suitable for the kind of problems that we have in mind. This is really the right time to do that, because experimentalists are very engaged and would like to talk to you about that. And the very last point is the fact that not only that we can solve these problems, but also maybe the quantum information science itself can help us to get better, deeper understanding about the nature of the theories that we're dealing with. Maybe we can even start from simple prototypes that are easier to simulate, but they still can reveal something interesting about QCD or nuclear physics systems that we didn't know before. And all of these directions are very exciting, and there are already a lot of good work starting in the community around these topics. And I imagine that in the next decade, we're gonna witness a lot of progress in all these directions. So thank you.
Thank you. Great overview. Right, so with this, let's move to Dima Kharzeev. Dima, did I pronounce your last name correctly?
Yeah, good enough.
Close approximation, how do you say it?
Kharzeev.
Yeah, okay, I cannot reproduce it, thank you. So Dima got his PhD in Moscow, and then he was an invited professor in Pavia, Italy, already very early, and worked at CERN with a one-year stop in Bielefeld, Germany, and became the head of the nuclear physics theory group at Brookhaven National Lab. He also became the head of the theory group of RIKEM, also Brookhaven, and became an adjunct. He also has an adjunct professorship at Yale. He is also now the director of the Center of Quantum Materials in Stony Brook. He has quite a list of honors and awards. I mentioned one, which is a Humboldt Prize by the Alexander from Humboldt Foundation. And interestingly, Dima has also 2 patents. One patent on graphene spintronic devices, and there's also a patent on a chiral qubit. Yeah, so very interesting panelist. And I'm looking forward to your 5 minutes, Dima.
Thank you very much, Christine. It's a great pleasure for me to be here and to have an opportunity to discuss the quantum directions for nuclear and particle physics. So as Christine said, I'm a theorist working on nuclear physics, quantum field theory, and the physics of chiral and topological matter, which is at the boundary between nuclear physics and condensed matter physics. And I first got interested in quantum information about 10 years ago, first as a purely theoretical tool, because it seemed to me that just reformulating some of the old problems of QCD in this language may be beneficial for trying to find solutions. So later on, of course, a very impressive development of quantum technology enabled the real simulations of some of the processes which are of interest for us, and we are now also started to perform this digital quantum simulations using the IBM quantum computer. So even though we are quite far from, reaching quantum advantage in all of these problems, I still think that this is a very interesting new direction which can help us to find solutions to problems we've been interested in for a while. So one problem that every nuclear physicist is excited about is confinement of color. And I really think that this is the ultimate realization of entanglement because the quarks are not only entangled, they cannot even exist as separate particles. So to me, this is the ultimate entanglement. And you may say, well, these are just words, but just thinking about it in this way brings up some interesting questions. So for example, we use Parton model in high energy and nuclear physics. And Parton model seemingly ignores the entanglement and deals with individual partons. It deals with probabilities rather than amplitudes. You just have factorization formulas, which is just a convolution of probabilities. And so at first glance, this thinking is completely orthogonal to entanglement. So I think this is a very interesting problem, understanding what really is going on with the wave function of the hadron. And this is the problem that a number of people and groups are currently working on. And one possible solution could be that if we perform, let's say, deep inelastic scattering on a proton, then deep inelastic scattering probes only small spatial subregion of the proton. And when you probe this subregion, you do not have access to the entire wave function or density matrix of the proton. You only have access to some subsystem, which is marked A here. And because it's only part of the proton, there is a non-zero entanglement entropy associated with this measurement, with this deep inelastic scattering experiment. And so the natural question to ask is whether it's possible to relate the corresponding entanglement entropy to the Parton distribution function, whether or not this entanglement entropy can be related to final state hadron entropy. And I don't think we have, the ultimate final solution to this problem. But these investigations have begun both in theory and in experiment now. So another exciting possibility with quantum simulations is that one can perform real digital and analog simulations of real-time QCD processes at the moment using some simplified models of QCD. Such as the Schwinger model, which Christine, Martin, and other colleagues pioneered. And in particular, one can perform real-time simulation of some phenomena which are of great interest for nuclear physicists, including chiral magnetic effect. So this is what we have done recently with my collaborator, Yuta Kikuchi. And this is something where you can really gain quite unique and new insight. So let me just, before I summarize, let me mention just one example. Consider E plus E minus annihilation into a pair of quark and anti-quark jets. So quark and anti-quark are correlated in spin, in color, so they are clearly entangled. And because they are also confined, you really produce a lot of entanglement, and just studying how this entanglement spreads in space-time is an interesting problem which can be addressed using quantum simulations, and that can inform new experiments in this field. So let me stop right here because my 5 minutes are up.
Yes, so true. So thanks a lot. That was very interesting. Especially, I liked especially the slide about entanglement. And so with this, let's directly move on to Joseph Carlson. So Joe, here you are, got the PhD at the University of Illinois. And then he was a Robert Oppenheimer Fellow at Los Alamos National Laboratory. And well, now he's the group leader of the Nuclear Particle Astrophysics and Cosmology Group at the LANL Zohreh Division. He's also a fellow of the American Physical Society. And one thing that I want to point out specifically is that Joe received the Heschbach Prize for, I'm quoting directly, for pioneering the development of quantum Monte Carlo techniques to solve key problems in nuclear structure physics called atom physics and dense matter theory of relevance to neutron stars. So, Joe, let us hear what you think.
Okay, thank you very much.
We can see your screen. Good.
Yeah, I just have a few remarks which have significant overlap, of course, with what many people have said before.
That's fine.
My perspective is more nuclear many-body theory, and actually from few to many-body theory. And of course, it's very exciting what quantum computing and quantum simulation could bring to nuclear physics. I mean, we really are lacking in ways to calculate real-time quantum dynamics. I think this is not a specific issue for nuclear physics, but basically all areas of physics. We have very good methods for some low energy experiments, low energy scattering, and also very high energy scattering, but there's a huge regime in the middle, which is difficult to access. The other thing that I really like about quantum computing and quantum simulation is that we're developing connections to quantum information science more generally. We're learning a lot about different approaches to dynamics in quantum systems, exact versus mean field, and also, for example, quantum to classical transitions. And then there are, of course, direct connections to many other areas of physics and chemistry and quantum many-body theory, which, of course, I appreciate. So I just wanted to bring out a little bit about the kind of things we're working on and why we think it might be interesting in the near term. So in the near term on NIST devices, there are of course limitations on the number of qubits, the practical depth of circuits given the errors that are involved. Partially for that reason, and also just because they're very intriguing by themselves, emulators and simulators, so both cold atom experiments, molecular experiments, and the classical hardware will continue to play very important roles. I mean, I think I've been very intriguing results from looking at nuclear physics and its relations to cold atom in particular. The fact that we have a modest number of qubits means it's probably a little bit easier to do a few body problem to start with, potentially embedded in a many body problem, as I'll discuss. And the modest circuit depth kind of corresponds to short times or higher energy. So in nuclear physics, just meaning the energy around the Fermi energy or above. So we've looked some at neutrino nucleus scattering or nuclear response. I mean, electron scattering also, of course. This is, I think, generally agreed. This kind of thing, the response functions are likely to be one of the earlier areas where we could reach an advantage with quantum computing, just because the time is required is not very long, and just like deep elastic scattering, if you're only looking at the inclusive response, you are really just probing a fairly small area of the nucleus. So we've looked at some simulations of this, algorithms and simulations for neutrino nucleus scattering. We have a few papers on that. The models are, to date, extremely simple, just foresight lattices and things, but it's nevertheless very intriguing. I put a couple of references here just so you could see what is standardly done in classical simulations, normal high-performance computing simulations. There's a paper here. Normally what we do is imaginary time correlation functions. I mean, that's just like lattice gauge theory or other many-body problems to get information on the response. But we've also looked at what you can get out of very short time propagation, and Zohreh Davoudi at Washington University in St. Louis in this particular worked on that. And you can actually get a lot of physics out with just of order one step. I would like to say Trotter step, but in fact, it's more sophisticated than that. There's a lot of intriguing, more general physics that can be studied in these systems, quantum to classical transitions, and how that evolves with time, and of course, how the entanglement in the system evolves with time, and with the observable, how inclusive it is versus how exclusive. We've also started to work on few nucleon scattering on a lattice with 2 and 3 body contact interactions, just tuning the 2-body interaction to unitary. Nuclear physicists will be aware of the relationship between this and Panelists effective field theory. And for very small systems of 3 or 4 particles, you can compute the real-time evolution classically. But we really would like to be able to use a quantum computer to do much bigger systems. There's a lot of questions that have to be addressed in addition to the preparation of the initial state and the time propagation. How do you measure the final states, particularly on what will initially be a fairly modest lattice? So how big a lattice do you need? How do you measure things that we know and love, like total and differential cross sections for exclusive final state? And of course, connections to things like entanglement and the time evolution. We're also looking at problems that come up in dense neutrino environments like supernova, neutron star mergers, and the early universe. This is basically at its core a quantum spin problem. You have a Hamiltonian, which have one-body terms, which are the standard vacuum and MSW terms. But then you also, in these dense neutrino environments, have a neutrino-neutrino interaction, which couples neutrinos which are propagating in different directions, and it can exchange flavor or neutrinos versus antineutrinos. There's a lot of correlation here with condensed matter spin models, which I find intriguing. And for example, Alessandro Ruggiero has been teaching us about the dynamics of entanglement and quantum phase transitions. How does this evolution depend on the initial conditions? And that also here, mean field versus the full quantum evolution of the 2 to the n particle states. So we're very intriguing and interested in all that. Finally, let me just say, I really like, this is such a popular field with young people. That's fantastic. And a lot of them are great. And that's wonderful. In particular, we've been working with Alessandro Ruggiero at the INT, Alessandro Baroni at Los Alamos, and Andy Lee at Fermilab. And we've also involved a lot of students at University of Tennessee and Michigan State University. And of course, this is enabled by the fact that the funding agencies have been pretty good about crossing boundaries between different offices, which has really helped. So our efforts are supported by DOE Office of Nuclear Physics, also DOE Office of High Energy Physics, and the Quantum Science Center that Los Alamos is involved in, headed by David Dean at Oak Ridge.
Yes.
So let me finish there.
Thank you. Thanks a lot. That was very concrete. And also pointing out how now we're in a time at which money can even cross interdisciplinary areas, like money can cross the boundaries between disciplines. So this concludes our block number 1, and we can dive immediately into our second block, in which we will have a discussion all together. And the first question that I'd like to ask you is basically a question that you also already touched on, especially Zohreh, but I'm still going to ask it to launch our second part. And that's basically, asking for holy grail questions. Suppose let's put ourselves mentally in a frame where we think we have a big quantum computer, very well developed quantum technology, lots of qubits, fully error corrected. Suppose you have all of this at your disposal. What are the holy grail questions that you would like to address? So I'm not talking about benchmarking science questions. Like these questions we know the answer to, we might ask them in order to benchmark and test our algorithms and hardware. No, I'm thinking about an era when we have like a quantum device that we can trust. And so what are the type of problems that you would like to tackle? And most importantly, what new physics could we learn? Who wants to jump in on that?
Maybe since I kind of mentioned some of these problems, I'll go ahead. So for me, I mean, this problem of non-equilibrium QCD is very interesting. The fact that we sort of have been limited and not really looking into kind of interesting things that can happen even in our experiment, right? This heavy ion collision experiment, and how sort of matter from some extreme condition evolves to what we measure in our detectors, and sort of tracking down that process from the fundamental interactions, and then maybe hopefully learning something along the way that has not been in our radar and described by the standard model, maybe pointing to something more fundamental and unknown. I think that would be really a dream for many of us, right? But I mean, going back to sort of other problems, just trying to do a computation in either quantum field theory or in quantum many-body problem for nuclear physics, and try to avoid a lot of assumptions that we make because we don't have enough computations to do them, right? I mean, like the problem of neutrinoless double beta decay, it's a very sort of long-standing, very challenging problem from the perspective of computations, because not only in this problem, but in many other new searches with using nuclear targets, we are really using large nuclear isotopes. And that's where computation is hard, but experiment is kind of facilitated by this larger sort of coherent effects in nuclear isotopes. So the theory is difficult, but there is more hope to get a signal. And therefore, on the theory side, we have to really work hard. And a lot of times there are so many models involved and so many approximations involved. And we are having this dream of making this program of computing, for example, the relevant nuclear matrix elements for these processes, using sort of the building blocks of a standard model and going through the systematic matching to effective field theories. But every step of the way is hard computationally, sort of trying to attack those problems and not have to deal with the signal to noise issues and things like that. That would be also a dream.
Yes. Yeah, great. So someone else wants to comment on that? Yeah, Dima wants to comment.
Yeah, so to me, a dream problem that I would solve using this dream quantum computer would be to understand how confinement works and how it is related to entanglement because QCD has a very non-trivial vacuum structure. It has these different topological sectors, and people start to understand how to use entanglement to detect topological order, for example, in topological materials. But in QCD, we are in 3+1 dimensions where topology fluctuates. You have topological transitions. And I don't think we really understand the relation between confinement and this structure of the vacuum. And this is where this dream quantum computer could help. But what I would like to add to this is that we don't have to wait till this dream quantum computer is here, because on one hand, we can use some simple effective theories related to QCD, 1+1 dimensional theories. And on the other hand, we can use the classical computers for computing things like entanglement in hadron wave functions. To the best of my knowledge, Zohreh can correct me if I'm wrong, no one has ever computed entanglement entropy inside the proton, for example. I'm aware of some lattice work on computing entanglement entropy of QCD vacuum, but I think entanglement inside hadron, which can be computed in principle using classical computers, was never done before. So, while we are waiting for this dream quantum device that Christine promised us, I think we can still, do some interesting work.
There's been a lot of sort of conceptual developments on how to define entanglement entropy and quantities like that for gauge field theories. This, you can imagine, is not a trivial question. But I think really that kind of theory development has to come first before we can actually start to compute these things and agree on them.
I agree.
Let me just reiterate one thing that was said before. I think the phase diagram and the dynamics of both the nuclei and QCD at higher energies and momenta is critically important. There's obviously a huge effort on the gravitational wave detector, and we'll learn a lot about the equation of state of dense matter from those observations. But we'd also like to understand the consistency with our theories, of course, directly with QCD, but as we use effective field theories for lower energy experiments, we'd like to make all those connections as well.
Mm-hmm. Yes.
Can I add a very short
Sure.
comment?
Yes,
I have a question to Joe, because I mean, he's an expert in really pushing very hard calculations on the nuclear physics side for these atomic nuclei. And so is it fair to say that before we actually get these quantum computers for problems that we've already started to attacking, we will be able to make quite good progress with classical computation? We will be able to really compute nuclear matrix element in germanium with high accuracy and precision before we even have to think about casting this problem into quantum hardware?
Well, yeah, that's an interesting example. I mean, I think there's a lot that can be done and is being done with classical computers, and I think this problem is being taken seriously now, and there'll be a lot of progress. But there's a particular part of that problem where there's a short range new interaction in the effective field theory, which is so far unconstrained. So you have to bring in elements there, which probably depend more on higher momentum physics. So I don't think we really know the answer to that, but there's a lot of things that can be done, of course.
Wow.
And I think there's a lot of progress on low energy structure and very low energy reactions, but once you get to dynamics, that's always extremely hard with classical computing.
Someone else wanting to add something on Holy Grail questions? while we are still in dreaming mode? No? Then, I mean, we can already dive into the second question, into which you lead it in automatically already in your answers. And that's looking into the next 5 to 10 years, right? So in the next 5 to 10 years, we will hopefully see even more development in the quantum hardware. We will still be in the NISQ era, but we will have larger, bigger, better quantum devices. So which would be the interesting problems that we want to address then? Yeah, so and which milestones will be important in the next 5 years? And which challenges also do you foresee? So which are the interesting problems we want to address in the next half decade? Which milestones do we want to hit, and which are the challenges, both technically and conceptually? Your opinion, dear panelists.
I don't want to be the one to go first all the time, so I'll wait.
I think you should go first.
Okay, so maybe I'll, from my perspective, interested in developments of lattice gauge theories. I think the next 5 to 10 years really is essential in putting together that theoretical framework that is kind of missing, right? I mean, it really requires a different theoretical eye to this kind of problems that we've been computing so far in lattice gauge theory. And in particular, just thinking about the Hamiltonian formulation of the lattice gauge theories, and whether we should still think about this sort of lattice-sized approach or other approaches that are maybe more suitable for quantum simulation. And if that's so, how do we actually come up with the most efficient formulation, Hamiltonian formulation of these theories? And even so, we have to then come up with the best algorithms and the most efficient algorithms that represent this complicated Hamiltonian framework. So I think one really important thing that should happen and kind of is happening at the moment, and I'm learning from a lot of very talented young people in my group, sort of teaching me on the Hamiltonian side of things, because I've been very much involved in thinking about quantum field theories in a finite volume and the action sort of approach to the quantum field theories, and kind of starting to learn that perspective and understand how now we can do better computations or quantum computations with this new language. I think these developments would be essential, and they would be happening in the next 5 to 10 years.
Yes, and we on our side, we need to get more comfortable with the action formulation. I noticed because, then we will be able to talk more efficiently.
I agree.
Yeah. Okay, that's a challenge. But someone else wants to add on challenges that we're going to face, and Dima, milestones.
Yeah, so I think in the near term, next 5 years, realistically, of course, we will not be able to study QCD on a quantum computer. But the good thing is that to explore, for example, the topological structure of the vacuum of quantum field theory, you don't necessarily need the full QCD. You can start from much simpler models. So just to use as an example, the Schwinger model that, is very familiar to Christine.
Close to my heart, yeah.
Yes. You do have topological fluctuations in Schwinger model. So the what we call in QCD Chern-Simons diffusion rate in the context of Schwinger model would be what condensed matter physicists would call electric susceptibility fluctuations in electric field. And you can really work out these things in simpler theories, put them on a NISQ device, understand how to do it, and then, once better quantum devices, either digital or analog, become available, we will be better prepared.
Yes.
So that's what I will do in the next 5 years.
Yeah, someone has a plan. Okay. Yeah. Yeah, Joe.
Yeah, I think sort of iterating a little bit on what's been said. I think the next 5 to 10 years is going to be building infrastructure for carrying out some of these computations, at least on a smaller scale. Speaking from a very small, limited experience on my end, there are some questions that on paper appear very doable to say, oh, this is a very simple system to put into a quantum computer. And then when you look at the details of how exactly do you set up your Hamiltonian so it translates into something that a quantum computer can understand, not to mention execute, requires a steep learning curve, and a lot of times you're building your own way in order to compute that. And I foresee that a number of academic and possibly even industrial groups developing tools that are more readily available to the community to allow that transition better. So you don't need to be an expert all the way through to the end, but if you're interested in a particular problem, you can execute it. And there's a little bit of that already appearing on the surface. So sort of thinking in the next 5 to 10 years is developing that infrastructure as tools for doing these kinds of computations with the hardware that we have at current time.
Mm-hmm. Yes, yes. Oh, yeah, Doug.
So let me just maybe bring a bit of an instrumentation perspective to
Yes,
the
please.
next 5 or 10 years. I think that one of the directions that people are already going, but that where we may see some progress is in adapting various low temperature sensors that have really great sensitivity and potentially energy resolution to detect charged particles. So typically these detectors are now used for detecting photons usually, or in some cases phonons. And I don't think yet have any real demonstration of their use for sort of the bread and butter of nuclear and particle physics experiments, which is detecting charged particles. And so there are all kinds of challenges with typically experimentalists are greedy, so they like lots of spatial resolution in addition to energy resolution. So that means arrays of such detectors and being able to read out those arrays and so on. And so just as Joe is suggesting that there needs to be sort of a building of infrastructure, there probably needs to be a building of infrastructure associated with this instrumentation as well.
Mm-hmm. Yeah, okay, great. Thanks for bringing in this perspective. So with this, actually, in 5 minutes, we will start taking questions from the audience. So if you're in the audience, you can start thinking about your question already now. And while you're doing this, I'm going to take one more round so we can go and have each and every panelist make a last 30-minute statement for concluding this block. And to inspire your statement, I'd like to ask you a question which is about expecting the unexpected. Okay, because yeah, every time a new technology is developed, then this really has the potential, and it has happened many, many times in the past, to have some new and unexpected, unforeseen discoveries, right? So just simply because you have new tools. Yeah? And so if you just take a wild guess, I mean, all we can do is make a wild guess, no, because here I'm asking you to expect the unexpected, no, but where do you believe could be the richest potential for finding or making unexpected, unforeseen discoveries in all this process of new algorithms and quantum computing, sensors, and understanding entanglement? What do you think? And we go in the same order as for our intro session. So actually, Joe Formaggio, Joe, if you're comfortable with starting, do you want to begin?
Okay. One thing that I don't know if this will pan out or not. There's a lot. There's a lot of research currently taking place in tuning basically single atoms, which are considered right now, individual qubits in a small quantum computer. Being able to use them in order to do some small scale calculation, but you're able to tune the coupling between the two sites in question. So, right now I think it's limited to nearest neighbors, but people have been able to tune the interaction between two different sites. And that appears to me as a new lever arm we have not ever used really that well before, where we artificially change coupling constants between quantum entities and observe what happens. And I think that if there's going to be a potential new discovery about, entanglement, or how forces interact, maybe even at the individual, at the fundamental level, it may come from studying these artificial lattices where the coupling strength can be tuned to one's desire, and doing that in a novel way.
Mm-hmm.
Throwing it out there.
Yes, thank you.
Maybe that already happened and I'm just shy on the literature.
So Doug, what do you want to throw out there?
Well, perhaps a sort of a related point. I am guessing that there are a number of things still about entanglement in multi-body systems that we don't understand and where we're probably missing some big features. And so, in terms of sort of a practical place where this might come in for an experimentalist, at least, if we start trying to squeeze spins for EDM experiments, I have a feeling there may be better and worse ways to do that as one prepares an entangled initial state. So that's my comment about what I think where we're likely to see a surprise.
Mm-hmm. So Zohreh, where do you see possible surprises?
This is probably the hardest question of this round. So I'm just wondering on a few things. I'm just, for example, given that we have expertise in both simulation and sensing, especially in the nuclear physics community, are there areas for which we can actually merge these two and kind of learning something new in the process? Can simulation help with the sensing and the other way around? I mean, of course, we know sensing is useful, for example, in doing quantum measurements and things like that. Can we actually develop this connection further now that we have both experts in sensing and simulation in the same community that talk to each other? I think that would be kind of interesting to watch and see whether people would start exploring this. And of course, again, I mean, this entanglement, everybody mentioned this. I think this is one of the topics that we have kind of not really explored enough in QCD, just trying to understand And where does this sort of entanglement comes in when we think about all sorts of interesting things that happen in QCD, including chiral symmetry breaking and confinement, deconfinement phase transitions, and all sort of things that, again, I mean, it's related to phase diagram of QCD and all the phase transitions and so on and so forth. Can these quantum information tools help us to shed light on some of these aspects that we kind of understand them in a different language at the moment? I really look forward to seeing how this thing develop over the next few years, as smart people have started to think about this.
Yes, 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 yes. So Dima, do you feel like embarking in some wild speculation?
Yes. So just to give a concrete example in response to the question that you posed, to me, a big discovery would be, for example, detecting the link between confinement and topological structure of the vacuum using entanglement. Because at the moment, what we know is that instantons, which describe these topological transitions at weak coupling, are not capable of providing confinement in QCD, but instanton picture is limited to weak coupling and semi-classical description. And we have no idea what happens at strong coupling when, you know, quantum fluctuations are large and are not at all described by semi-classics. And this is something which I think in principle one could detect using the methods of quantum information and quantum simulation. So if such a link were discovered, to me it would be a great breakthrough.
Yes. So, Joe Carlson, you have the last word of this blog.
Well, I will use it to just maybe reiterate some of the things that have been said. Particularly, I think we'll be surprised, will be the capabilities of simulators, cold atoms, molecules will be very important, and particularly understanding real-time dynamics. For example, the behavior in quenches or changing the couplings, as Joe Formaggio mentioned. I think we can hope for a much more fundamental understanding of quantum dynamics and how it's related to the underlying interactions.
Mm-hmm. Yeah. All right, thank you. So we conclude this blog and then we can have some questions by the audience, which is watching now. So if you're in the audience and you want to ask our panel members a question, so please use the raising hand feature. Then I will see that. Oh, okay. Peter Jacobs wants to ask a question. Please go ahead.
Yeah, one aspect of QCD that I didn't hear discussed today, and maybe I missed it, is that of jets. Jets are fundamental to QCD, studied extensively and, you know, in perturbative regime, extensively experimentally, and intrinsically quantum mechanical in their nature. Their internal structure is governed by interference. So I'm wondering whether, you know, jets are a useful benchmark, if you like, one that you don't require, you know, these kinds of, you know, techniques to calculate, but nevertheless are amenable to it, and whether this is a good direction to go, and if so, if people thought about it, how one might actually address that problem.
So, Dima.
Yeah, this is a great question. And in fact, jets were the last example on my slide. So the point is, for the sake of argument, imagine quark and anti-quark jets produced in a plus and minus annihilation. So in traditional perturbative TCD treatment, you just introduce fragmentation function for quark jet, fragmentation function for anti-quark jets. They are purely probabilistic evolution equations which describe these jets, which do not at all know about quantum entanglement between the parent quark and anti-quark. So this is completely neglected in traditional perturbative QCD scheme. And so what I think would be extremely interesting is to look at correlations between this quark and anti-quark fragmentation, which would be sensitive to the quantum entanglement between these jets. I'm not aware of such studies done before, and I think it's a really interesting experimental and theoretical direction.
Dima, it sounds like you have particular observables in mind. Perhaps we connect offline.
Yes.
I was muted. Okay, so thanks for the question. Does someone else want to ask a question? Please raise your hand. I don't see any hands raised. Oh, yes. Yeah, please ask.
Yeah, this is Sanjay Reddy, and I think there's widespread acknowledgement in the nuclear physics community that finite chemical potential, low temperature QCD is the holy grail for low energy physics with very broad implications for astrophysics and cosmology and gravitational wave astronomy. What are the trends that we are seeing in quantum computing today that inspire confidence that in maybe 2 decades or so, we would have solved QCD at finite temperature, at low temperature, but finite chemical potential using quantum computing and quantum simulations?
I can say a few words. I don't know if it would be convincing for Sanjay. Hi, Sanjay. So I think like with regard to the chemical potential, if you look at some of these Fermi-Hubbard model calculations, I mean, including chemical potential is in the Hamiltonian formulation is really no problem, right? I mean, you can treat that term in the same footing as the other terms in your Hamiltonian. And as long as you know how to do the rest of the quantum simulation, then that chemical potential term is not a problem. And in fact, you can also introduce that in say gauge theories and or quantum field theories. The part that is less trivial is actually the temperature part, right? And trying to prepare a Gibbs ensemble, given the fact that sort of now you're thinking about an imaginary Hamiltonian time evolution to sort of implement that preparation of a Gibbs ensemble and introduce a temperature into the calculation, that's more non-trivial in a sense. But there's been quite great progress on that front as well with regard to this Gibbs ensemble preparations and introducing temperature for the spin systems and so on. There are several proposals out there. Some of them have been benchmarked. So I think sort of merging the two aspects, the finite chemical potential and finite temperature, that's going to be sort of that's going to be doable, I think. But the finite temperature part is probably more challenging than the chemical potential. That's my viewpoint.
So am I to understand that the 0 temperature finite chemical potential QCD phase diagram is within reach?
If we understand other aspects of the problem and we know how to translate this QCD in a Hamiltonian language to quantum hardware, yes, then we can also deal with the chemical potential term. But of course, there are so many other developments that have to happen before that. So.
Mm-hmm. Thank you. Thank you. Oh, Elliot Rosenberg has a question.
Hi, so thank you for the great discussion, and please forgive me for asking a question that's well outside of my own area of expertise. But I was wondering whether if we had like quantum computers with error correction and many, many qubits, whether they could be useful for nuclear fusion. Could we like simulate nuclear fusion and figure out how to do that more efficiently using the quantum computers.
I mean, one comment is that in principle, any computational problem that you can do with a classical machine, you should be able to do with a quantum machine. There has to be an efficient representation on algorithm for that problem. But that being said, doesn't necessarily mean that the best way to proceed is to take your computational problem and turn it to some quantum gates and perform the calculation in that way, because I mean, in that sense, then we are, for example, led to do the same sort of action-based computation or Monte Carlo computations that we're doing on a classical machine, trying to translate that on a quantum hardware, which is of course not what we're trying to do. We're trying to leverage the intrinsic capabilities of a quantum hardware that would allow us to actually do real-time evolution of these systems. So we change sort of the framework. So I'm not very familiar with these fusion problems, but presumably there has to be a similar trend here, that maybe some of the ways that we're doing this classically, we can avoid them and think about how to transform that problem to a language that is more intrinsic to a quantum hardware. Otherwise, you're not going to see the quantum advantage quickly.
Mm-hmm. Do we have more? So thanks. Do we have more questions? Oh, there was one, but then it disappeared. Oh, now we have two. Okay, so now I don't know which one came first. Xu? I'm sorry if I mispronounced your name. Would you go first?
Thank you. Yeah, this is Nushu. Yeah, I have one question. Maybe you will feel. Can someone explain that why a quantum computer is much better than classical computer? So this is one. And secondly, is there a projection when we can use a quantum computer for data analysis? For example, now we use around 2,000 cores to do data analysis for rig data. So, okay. Maybe it's a silly question, but you look puzzled.
Who wants to take the question?
The first one is more important. Projection, I guess, is hard, even for theorists, but.
I can make a quick comment about maybe the second question that it's probably not your priority in terms of the two questions. But one thing to notice is that there are optimizations, which is an important problem, right, for classical sort of data science. And you can leverage sort of quantum hardware, even the NISQ era quantum hardware, to facilitate the optimization problem. And even there are approaches now to quantum machine learning, given the same kind of fundamental quantum subroutines to these processes. So that's kind of already started. And in fact, for example, the CERN physicists are really looking into this, of like in the era where you have to deal with a lot more data that they already deal with, right? Can you leverage quantum hardware, even NISQ era quantum hardware in the next 10 or 20 years of this program to do things a little bit better and faster? So yes, that's something that people are thinking about very seriously.
So 10 to 20 years, is that what you're saying?
Even now, I mean, people are coming up with ideas and protocols for leveraging these systems. But I'm just saying that this would be something that maybe if you think about the 20 years of the program at CERN, where you are expecting even more data and more complicated signatures to look for, then it makes sense to think about new paradigms in data analysis.
The second question comes from when I read some articles say you have 1 qubit to do a calculation, you may need 5 to do the correction to understand the error. So that's why I asked. All right, who can help me on the first one? Dima?
Well, let me just say the obvious thing. So quantum computing is especially well suited for real-time processes because, you know, you really have the evolution operator. And they are good for processes, for example, finite band density, where traditional Euclidean simulations are hard. So we obviously are quite far from any kind of quantum advantage in doing QCD in this real-time quantum computing. But the promise, I think, is very significant, and you know, the technology develops, you know, at such a pace that, who knows, maybe in 10 years, quantum computing will be the way to do real-time QCD dynamics. But, you know, I cannot promise you that.
Yeah, there's so much that could be said on this. So thank you. But it's also time to conclude. Yeah, so we finished our 90 minutes, unless someone of the panelists has something on their heart they want to share before we wrap up. No? Yes? Zohreh has.
No, I already talked a lot, so
No,
I don't
please.
take the time. No, I just said to address the question, the last question, I just wanted to say that nature has a lot of phases and loves the phases, and these are the things that are very hard classically to keep track of. And it's great that the quantum hardware can keep track of them for us, so we don't have to do sampling and not being able to really take care of them properly. So that's really, I think, one of the main powers of the quantum hardware that really acts in the same way that nature does. So it really facilitates the computation for us in that way.
Yes. Yes.
Thank you very much.
Yeah, that's actually a great concluding remark. Thanks. And yeah, so for me the most exciting part of today's discussion was when we talked about like this ultimate perspective, yeah, where we could possibly go. And yeah, sorry, you talked a lot also about the real time, and Dima talked about real time. Joe mentioned on the perspective to maybe with experiments get a better hold on understanding dark matter, and to dive into, yeah, the fundamental and unknown. And it would be extremely exciting to maybe one day really address the questions that are not properly answered by the standard model, right? And yeah, also like the puzzle of the missing antimatter. And I want to finish here with a quote that actually Natasha Waxman, who's someone here at Parameter Institute, pointed me to. And it's by a Canadian singer, Leonard Cohen. So he said, it's the cracks where the light comes through, right? So it's where a theory fails or where a theory cracks or it doesn't explain properly. It's where we really have this opportunity for discovery, yeah, of finding new physics and gaining new understanding. And I hope that quantum methods in one way or another can play a role in just that. Yeah, so thank you. Thank you to everyone.